So this is all about conservation laws, right? So these are the conservation laws that we're familiar with, right? So there's charge, right? So when you look at the things like a pi plus, right, that's just a positive charge. The only one you got to memorize is a proton. A proton is positively charged. Charge is going to be conserved, right? The other things that are conserved are in a decay, we need to conserve mass and energy. Right? Because remember, energy can turn to mass and mass can turn to energy. But if you have a decay, you can't have an electron decay into a tau. Okay? Because a tau is much, much larger than an electron. So that can't happen. But a tau can decay into a muon and an electron. Okay? Like, all these things, right? It can, and there have to be other particles, but to be sure, you can't decay in a decay. And a decay is when you've got one particle on one side and you've got many particles on the other side. Okay, that's a decay. That's how you know it's a decay. So mass energy in a decay, definitely you can't decay into something that's more massive than you. Okay, there's baryon number, right? So baryon number is decayed, and then there are lepton numbers that are conserved. So there's the electron number, there's the muon number, and there's the tau number, and these things are independently conserved. Okay, so whatever it is on the left side will be the same as the right side, and this is how we can somehow tell, what the decay products are. Okay, and then there's also strangeness. I'll go strangeness. I started to make a number sign there. Strangeness. Okay, so strangeness is sometimes conserved. Okay. If you're creating new particles, let's say you go, you slam a proton plus a proton together, there's no strangeness on this side, so there has to be zero net strangeness on this side. Okay, so if it's a particle collision like this, and we are, by the way, this would be a strong interaction, strangeness is conserved. Okay, so here it's conserved. Okay, but the strangeness number, if it's a decay, if you've got some strange particle, it can decay into non-strange particles. This is, by the way, a weak interaction. Okay, so strong interaction is we slam proton into proton, right? Okay, and they exert the strong force on each other. Then strangeness is, you can't, like, protons are not strange, so you cannot create a net amount of strangeness. And these things are all just numbers you look up. Okay, which was why this wasn't maybe my favorite thing, but I kind of like particle physics now and I want to know more about it. Okay, so there that is, right? Those are our conservation laws, and then the question is, what are all these particles, right? Well, you've got the force mediators, right? These are the elementary particles. The force mediators are, well, for the electromagnetic force, it's just a photon, okay? For the weak nuclear force, we've got W plus, W minus, and Z naught, right? For the strong nuclear force, we'll just say they're gluons, right? Sometimes they'll say like pions or something like that, but that's like an old model. Really, we call them gluons, and it's kind of beyond so strong nuclear force is mediated by something called gluons. So these are fundamental particles, okay? Then there are leptons, right? So there are all of these particles and their antiparticles. So we've got an electron, right? And the electron neutrino. And we've got the muon, which is just a fat electron. Muon is just an electron that's a little more, got more stuff, And there's the muon neutrino. Then there's the tau particle, okay, and its neutrino. Now remember, these neutrinos they are leptons, they have a lepton number, but they have no charge. Like literally the word neutrino means small neutral thing, okay? These guys have charge, these guys don't have charge, but they all have, this has a lepton number of 1. This has a muon number of 1. These both have a tau number of 1, and they're antiparticles. Everything about the antiparticle is negative. It's the opposite. Okay, everything about the antiparticle will be opposite. So for example, a matter strange particle is -1. The antimatter strange particle is +1. Okay, Just there it is, right? Okay. Okay. So these things are fundamental particles, right? Then you have quarks, right? You've got up, down, top, right? Or sorry, whoops. Up, down, top, bottom, strange, and charm. And I think I've got them in the wrong place here. Okay. But you've got these 6 quarks, right? And those quarks will make mesons. So if you've got quark, antiquark, that's a meson. If you have quark, that is a baryon. Okay, so these things are not, baryons and mesons, hadrons in general, are not fundamental particles. Okay? All right, so that's sort of, we talked about that in class, and then for the pair production events, it creates an electron-positron. What conservation laws are followed? Well, to understand, you've got a photon, right? The photon comes in and it goes next to a nucleus. It creates an electron and a positron, right? Well, the first thing that's conserved is charge. This is 0 charge, and this is 0 net charge, right? -1 + 1 is 0. So charge is conserved, right? That's the first law. The second one is mass energy. In fact, this is how we solve these problems, right? If this is 3 MeV, right, then the equation looks like this. 3 MeV turns into 2 electrons, so 2.511 plus 2 kinetic energies, right? So energy is conserved. And then the other thing that's conserved is lepton number. There's 0 electron lepton numbers before, because photons are not leptons. And then afterwards, the electron is a +1, the positron's a -1. Okay, so since we created matter and antimatter in equal parts, we have not changed the lepton number of the universe. Okay, so 0 turning to 0 lepton number. Okay, and the same is true here. We can say the same thing, only here it's baryon number, right? So charge is conserved, right? A proton is positive, antiproton is negative. The energy from the photon turns into these, and it's a lot of energy, right? And then the only other difference is for this guy, the baryon number is conserved. This guy has a +1 baryon number. That one has a -1 baryon number. So we don't really create any net baryons or net protons. All right, and then what is the missing decay product? Okay, so let's look at this. Let's look at charge. Here, I'm going to do this. We're going to look at charge. We're going to look at, the only other numbers we've got here is L tau. So the tau lepton number and the mu lepton number. Okay? So you just go through. This has a charge of -1. We know that from the minus. These have 0 charge, right? And so therefore, this has to be -1. So whatever it is, it's got to have a charge of -1. Let's look at our tau number. The tau minus is a 1. This guy is a -1. Whoops. This one is a 1 for tau number. This guy is a 0 because it's a muon, right? So this guy is going to have 0 as its tau number. So it's not even a tau. That means it's not a tau. It's not a tau neutrino. It's not an anti-tau, and it's not an anti-tau neutrino. It's not tau in any way. Okay? So now let's look at the muon number. This is 0 for muon number. This is -1 for muon number. This is 0 for muon number because it's not a muon at all. It's a tau. Right? So what does this guy have to be? It's got to be a muon. So what muon has a charge of -1? Well, there are only 2 charged muons. There's the mu plus and the mu minus. This guy is the one, right? It's got a negative charge. And it has to have a negative charge. It also has to have a positive muon number. So it has to be this guy. So that's the answer. That's a mu minus, right? So let's look at this guy. Let's do the same thing. Charge. Here we're going to balance L mu and L electron, right? Because that's all we have here. If we had a tau, we'd add another column for tau, right? So charge, we've got -1, something, and 0. Well, this has to be 0, right? Because -1, that can't have any charge. Let's look at our mu number. This guy is -1, 0. This guy has to be 0 as well. So it's a charged particle, and it is a, muon number, sorry. What am I doing? I'm moving too fast. Okay, hold on. Here, let's see if can I erase? I can't. All right, good enough. So the muon number, this guy is 1. This guy is 0. This guy is 1. So therefore, this guy is a 0. Okay, but not because of the reasons I just said, right? Okay, so let's look at the electron number. This guy is not an electron. This guy is. All right, this guy is, we don't know. This guy is not an electron. So what does this guy have to be? I think it has to be -1. So what doesn't have any charge and has a -1 electron number? Well, the only uncharged electron things in the electron family are a mu, an electron neutrino, and an anti-electron neutrino. Okay? And so it has to be an anti-electron neutrino, doesn't it? It's the only one that has a -1 lepton number, electron-lepton number, and it doesn't have any charge. Okay? So it's got to be that guy. Which, eventually you're going to look at these and go, oh yeah, of course that's what it's got to be. Okay, so does it obey? Okay, lepton number, none of these are leptons, so yes. Okay, so now you got to look at your little hadron reference here. Okay, let's look at our charge. Well, that's +1. That's the only one you have to memorize. It doesn't P plus, right? This is -1, so there's 0 net charge, and this is 0. We know that because of the 0, right? And 0. So that works. Charge works, right? Let's look at our baryon number. Baryon number, well, proton is a baryon. That's the one I know. I don't have to look that one up. Okay. Pi, this guy, the pion, the pi minus is actually a meson, so it is not a baryon. All right. The kaon is, that's a meson. That's a meson. And when you look it up, it's the same as the ks and the kl. In fact, if you look at those, they're identical, and that's an interesting story. Okay, you'll have to look on Wikipedia why that is, and it's because I believe the kaon is actually indeterminate. Like you could observe it in either the strange or the L, the S or the L, and you don't know which one you're going to get. Okay, all right. So this kaon is not a baryon. Okay, but this lambda naught is. So it's a matter baryon, right? So baryon number is conserved. 1 on this side, 1 on this side. Okay, let's look at energy just for kicks. Didn't say to look at energy, right? Well, a proton is, what is a proton? 938. I'm doing MeV, right? 0.3. A pion, a pi minus, is 139.6. A kaon is 4, we're in trouble here, 497.7. And the lambda particle, boy, that's a big boy, 1,115.7. Now, this energy is on the right side is much more. But here's the deal, okay? We can get this reaction to occur. We just have to provide kinetic energy. We got to speed this guy up through many millions of electron volts, right? In fact, you can figure it out. Just add all this up, right? And then subtract this, and that's how many volts you have to accelerate this through. This is why we do energy in electron volts, okay? So you accelerate this through enough voltage, and you can get this reaction to occur. It's going to create a massive particle. Where did that mass come from? It came from energy, right? E = mc². So energy is okay. As long as it's not a decay that decays into larger particles than itself violates conservation of energy. This is a collision type event. And we could just give these particles enough kinetic energy to create the matter, right? So energy is okay. Okay, so let's look at strangeness, okay? And the strangeness, we can look this up in the reference here. Protons are not strange. Pions are not strange. A pi minus is not strange. A kaon, why, I believe it's got a little strangeness to it. That's a +1. Which means it's got, I think that means it's got an anti-strange quark in it, because I think the strange quark is -1. I should look that up before I keep saying that, you know. All right, and then this guy here, the lambda is -1 strangeness. So in this collision, we did not create a net amount of strangeness, so it's okay, it'll work. Okay, you can't change strangeness number in a creation event like this. Now you can decay and violate strangeness, but you cannot do it with a creation thing like this, where we slam particles together. Okay, or we're turning energy into matter. We can't do it then. That's a strong interaction. All right. Okay, so does this conserve charge? I think so, right? This is 0 turns to +1 and -1. Okay, let's baryon number. The kaon is not a baryon, right? Pions are not baryons, so they're not even baryons. And in fact, they're not leptons either, right? Okay, does it conserve strangeness? Let's take a look. A kaon is strange, and so it's +1. The k naught, okay, and then a pion is not strange. These guys are not strange. So it violates strangeness, but notice that this is a decay. Okay, so it's okay because it's a decay. This is a weak interaction. When it decays, it's interacting weakly. Okay, it's only when you create. So strangeness in a decay does not conserve. Strangeness is not conserved in decays. So the answer is strangeness is not conserved, but it still can happen because it's a decay. All right. And then let's look at this guy, the charge. Okay. The charge is, 0. Proton is +1, pi minus is -1, right? So charge is good. Baryon number. Let's look at the baryon number. Okay. And the lambda is, in fact, a baryon. It's a +1. Proton is +1. A pion is 0. So we're good for baryon number. Okay? Then let's look at lepton. Well, none of these are leptons, right? All right, so we're good for lepton. Let's look at strangeness. Okay, I believe the lambda has a strangeness number. It does, -1. Okay, protons are not strange. I know that. Pions are also not strange. So, again, strangeness is violated, right? But violed. Wow, what did I just violated? Okay, strangeness is violated, but it can occur. This decay can occur because it's a decay. Okay, because it's a decay. This decay possibly does occur. In fact, you know, I looked it up. Okay. All right. I think I'm done with words.